Okay, so in this problem, we're given a dam in the shape of a semicircle, as is given at the picture here. So the bottom of the dam is the bottom of the semicircle. And that semicircle has a diameter of 4 meters. It's not a really big dam, just about 16 or about 12, 13 feet across. You convert that to feet, so little tiny dam. And of course, the depth of my dam would, of course, be the radius, which since it's 4 meters across, the depth would be 2. So what we want to do is translate this picture that's given to us, this graph, into some kind of XY equation. And there's different ways to do that. Probably, if you can ever do it, especially when you're dealing with something like a circle, you really want to center it at the origin. So if I draw in my X and Y axes here, because of the shape I'm dealing with, it's most convenient to draw it so that the origin is actually in the middle of the top of the dam there, right there. Okay. So that we know we're dealing with a semicircle. We're actually dealing with the bottom half of the semicircle for a circle of radius 2. Right? Which means the depth down here, this bottom of the dam would actually, in our coordinate system, be 0 minus 2. So we need to find the equation of that thing and go from there. So since we have a circle and I'm centering it at the origin, then that would be x squared plus y squared equals the radius squared. Should be 4. Now, I'm drawing my picture so that, the way I have my picture here, so that everything is starting down here at -2 is the bottom of the dam, 0 is the top. So I do have to take that consideration here as I start talking about this integral. So I have to keep that in mind, that in the picture above, I did the bottom of the dam at 0, the top of the dam was my value A, and that's going to come into play here. But what we need to do is, again, measure the cross section here. Right, so we measure the cross section. Right? We measure our cross section here. Right, that's going to be my width function. And notice width is just going to be twice the radius of where we're currently at that depth. Well, I can solve this for x and get that x is equal to the square root, right? X is equal to the square root of 4 minus y squared. And in that width function w here would be 2 of those. Square root of 4 minus y squared. Again, the width is a positive function. That's why there's no negative sign. Even though the equation for this part would actually be negative square root, that's not going to matter here because the width function here needs a positive answer. The width function needs a positive answer. Okay. All right. And so now we can start computing our total force. So remember, force is just rho g times the depth times your width. Again, it was a minus y because that was the depth there. Here, if we're on some point, the depth is not going to be a minus y. Well, you can still think of it that way, where a here now is 0 minus my current y value, right? So that my depth is actually going to be 0 minus the value would be actually negative y, would be my depth. So force would be the integral from a to b of rho g times your depth, a minus y, times your width function, dy. So putting all that stuff together, we have our width function is 2 square root of 4 minus y squared, right? And we have our depth is just the opposite of whatever y currently is. That's the current depth. And our integral is going to actually range from -2 up to 0 along the y-axis. So putting all that together, we'll have force equals the integral from -2 to 0 of rho g, those are both constants, times minus y times 2 times the square root of 4 minus y squared dy. Okay, so now we're ready to start working through this. So the rho and g will just come out front. The rho and g there will just come out front. The 2 is a constant, but we're actually going to absorb that in just a moment. So let u be the inside there, that square root. Du is going to call for a negative 2y dy. And so notice here, I can take the negative sign along with my 2 in my dy, and I have everything I need to carry the substitution through. Okay, I have everything I need to carry the substitution through. So then we can compute this now as the rho g integral -2 to 0 of 4 minus y squared to the 1/2, and we have the -2y dy that we need to carry the integration through. So that means we're just integrating u to the 1/2. So to integrate u to the 1/2, we would add 1 to the exponent and then divide by it. So I'm going to have rho g. So for u to the 1/2, we'd add 1, which would make it 3/2, and then divide by it. So it's going to be times 2/3 times that stuff now raised to the 3/2 power. Evaluate it between -2 and 0. So then we set about computing that. Okay. So we're going to have 2/3 rho g, and then when we plug in 0 there, that's going to be 4 minus 0 squared, which would be 4 minus 0, be 4 raised to the 3/2. Remember, when you take something to a fraction, you can either raise it to the numerator first, then do the root, or do the root first. So for 4 to the 3/2, I would do square root of 4, which would be 2. 2 to the 3rd is 8. And then I'm going to plug in -2. Well, some nice things happen when we plug in -2. We're going to have y squared, -2 squared will be 4. 4 minus 4 will be 0. That'll be 0 to the 3/2 times all that stuff would just be 0. So we get 8 times 2 is 16/3 times rho times g, and then we can just multiply all that stuff out. Simply on a calculator, 16 divided by 3 times 1,000 for water, times 9.8 for gravity, and we get that it's 52,266. And 52,266.7, and our force unit is newtons. So that's the total force that's being pushed on this dam, being pressured onto this dam. So again, the idea here in this video is we need to first set up some kind of coordinate system so that we can talk about the different parts of our equation. In this case, we needed the radius because we had to double that to get the width. So I needed x in terms of y. So again, I centered at the origin. So width is double that. And then it's force is equal to rho g times the depth. That's what a minus y represents. In our case, it was, with our system, it was 0 minus y. So that's why it's negative y times my width function. Okay, we then did a little bit of integral substitution. Again, when we do that, this is really u to the 1/2, which means when you do the integral, you'd add 1 to it to get u to the 2/3, or 3/2, sorry, times 2/3. So that's u to the 3/2. But rather than writing out that step, I just paired up for my dy and just did it with the original function. Okay, and that way I don't have to deal with changing limits of integration or anything like that. Then we just work out the integral. And again, we find out here that it's 52,266.7 newtons of force.